Factor theorem. The factor theorem says that a polynomial function f of x has a linear factor x minus a if and only if f of a is equal to 0. And again, a lot of letters and variables and constants and labels. So I will give you an example and hopefully take you through what this theorem wants to state. And before we dig into the theorem itself, I want to go back to quadratic functions. And since you're very familiar with them, we can establish some of the definitions that we need to understand for this theorem. So I'm going to give you a function, a quadratic function, f of x. Let me grab my brush. I'm going to grab this function. F of x is equal to x squared plus x minus 6. Okay, and this is a quadratic function, and if you remember, we worked with these a lot. We sketched their graphs, we found the zeros, we found the y-intercept, the vertex, and we established if they were opening up or down, etc. And we were able to sketch a pretty precise drawing of what this function looks like on a graph. Okay, so we're going to use some of that today. We're going to remember when we looked for the x-intercepts. If I wanted to look for the x-intercepts in this function, what we did was we had to factor, right? Because x-intercepts I could find when y was equal to 0. So I would write that 0 is equal to x squared plus x minus 6. And if we were lucky, we were able to factor this. If we couldn't factor, then we had to use the quadratic formula, or we could also try the other method of completing the square. Okay, so in this case, I have 0 is equal to, and I'm going to try and factor this. When we factor this, we get x plus 2. I'm sorry, x plus 3 times x minus 2. Okay, so we have rewritten this function in the form of two factors. That's why we use the term factor the function, because we rewrite the function as two factors. And remember what a factor is. It's numbers that you multiply together to get you another number. So I can say here that if I multiply this factor times this factor, I will get back my original function. So these are factors of the function. Also, when I wanted to find the x-intercepts, I would take each term and use the zero product property rule, which says that if this times that is equal to 0, then x plus 3 is 0 and x minus 2 is 0. Okay, and we would solve for x. I hope this refreshes your memory. And then these numbers were the numbers that we would plot on our graph, because these are the x-intercepts. And remember, x-intercept means where does the graph touch the x-axis. So for this case, I had at x equal -3, I have a 0 here, and I have one at x equal 2. Okay, and what I want you to learn from this is that the factors of a function are also the x-intercepts, and they are also called the zeros of the function. They are also called the solutions of the function. Okay? Find the solution is finding the x values. Finding the x values is the same thing as finding the x-intercepts. Finding the x-intercepts is the same thing as finding the zeros. And why do we say 0? Because if I were to plug in into my function, if I evaluate my function at x equal -3, or if I evaluate my function at x equal 2, with both of these values, my function will equal 0. So these values are also called zeros of the function. When x is equal to -3, like here, my y value is equal to 0. When x is equal to 2, my y value is also equal to 0. So I just wanted you to see the different names that these values have, and they all mean basically the same thing. So from our factors, I find my x-intercepts, which are also my zeros, which are also my solutions to the function, okay? And very important that these are factors, because if I multiply these two together, I will get back the original function. So they are factors. And if you want to link what I've just explained with what you've learned from the division algorithm, these factors, since they are factors, if I were to divide this function by this factor, you know what the remainder is going to give you, right? You should have notion of what that remainder is going to be. If I tell you, or you find out that these two are factors, I can divide this function by this factor and I get a remainder of what? And I can divide the function by this factor and get a remainder of what? And your answer should be that the remainder will be 0. Okay? The remainder will be 0 if I evaluate the function at any of these two intercepts. So it all means the same thing. This factor theorem here tells you that a polynomial function has a linear factor if and only if f of a is equal to 0. And this is basically very, very similar to the remainder theorem. The remainder theorem said that if I divide a polynomial by a linear term like this one, then the remainder is going to be equal to evaluating the function at that term. The only difference with this one here is that the linear term happens to be a factor of the function, so the remainder is going to be 0, and that's what it's saying here. F of a is equal to 0. Let's do an example. This was just reviewing here. Now we're going to do an example from your book. In the example in your book, it says to show that x minus 3 is a factor of x cubed minus 4x squared plus 2x plus 3 by using the factor theorem. And it also says find q of x such that x minus 3 times q of x equals your original function. And that makes sense, right? If I take my quotient and I multiply it by my divisor, knowing that the divisor is a factor, then I should get my original function back. This is what I just said. If I have 12 divided by 3, this gives you 4 with a remainder of 0. That means that 4 and 3 are factors of 12. In this case, I have, whoops, I wrote a radical instead of a division symbol. If in this case I'm saying that this quotient multiplied by the factor has to equal the dividend. And you already know this from what we've discussed before, and that's what it's saying in this problem. Find the quotient so that when I multiply that quotient by the divisor, I get back my dividend. That's what it's saying. Okay, sometimes the wording can be confusing. Let me erase some of this. Okay. So now that you understand what you have to do, let's do it. Show that x minus 3 is a factor. How do we know when something is a factor of something? We know when the remainder is 0, then I know it's a factor. But I'm not going to use division because I already have a different way of finding the remainder, which we learned in our previous lesson with the remainder theorem. So if I want to know if this is a factor of this, I'm going to use the remainder theorem, which is a general form of my factor theorem. The factor theorem is a specific case when the remainder is 0. So let's see, if I use the theorem, what I need to do is I need to evaluate, well, let's go up here so that you see the theorem again. If the factor is linear, and in this case my factor is linear, right, x minus 3, if my factor is linear, then I should get f of a equal to 0. And a is this number here. So in this example, x minus 3 is my linear term. I have to evaluate at f of what? So remember, if it has to look like x minus a, and my linear term is x minus 3, then my a is equal to 3. Yes? X minus a 3. So in my specific case here, a is 3. So the factor theorem says that I evaluate f at that value of a, and I should get 0. If that's true, if I get a 0, then I can say that that term, that linear term, is a factor. Let's do that. So remember, you might be tempted here to do synthetic division and see what your remainder is in order to say if this is a factor or not. But since we already learned a new way of doing that, we can just go ahead and evaluate f of 3, because in the theorem it says f of a has to be equal to 0. So we're going to check that. In this case, a is 3. So f of 3 is equal to, and I'm going to substitute 3 in each one of these x's. So it's going to be 3 to the third power minus 4 times 3 to the second power plus 2 times 3 plus 3. Let's see if we get 0. 9 minus 4 times 9, which is 36, plus 6, plus 3. I did this wrong. 3 to the third power is not 9. I'm forgetting my multiplication. I'm sorry. I did 3 times 3 instead of 3 to the third power. And 3 to the third power is 27. So 27 minus 36 plus 6 plus 3, that equals 0. So I have proven that f of 3 is 0. That means that f of a is 0. And the theorem says that A polynomial will have a linear factor if and only if f of a is 0. We proved that f of 3 is 0. So that means that this factor, this term, is a factor. It is a factor. It says, show that it's a factor. How do I do that? Evaluating the function at the value a, and if it equals 0, it is a factor. Okay? And we use the factor theorem. I hope you understand this. The next part of this problem says that find the quotient. Now, to find the quotient, what do we do? To find the quotient, we need to divide. We need to divide this expression by this factor. You choose the method. You can do long division or you can do synthetic. I'm going to choose synthetic. So for part B of this problem, I'm going to use synthetic division to find the quotient just because it's quicker. So let's write out our coefficients. 1, -4, 2, 3. And the number that comes out here, remember I have x minus 3. So this is going to be 3. How do I find 3? You solve for x. You can do x minus 3 equals 0. X equals 3. Or you can also do what I showed you. If this has to be x minus c, then x minus 3, c is 3. Okay? Any of those two ways. Now bring down the 1. This is 3. This is -1, -3, -1, -3, and this is 0. We already knew that our remainder had to be 0. So if you do divide and you get a remainder different than 0, you've done something wrong because we've already proven that the remainder is 0. Remember, this is the remainder. This is also the remainder by the remainder theorem. Okay, so here's my constant term, here's my x term, and my x squared term. So this is x squared minus x minus 1. That's the quotient. Okay? So what they asked me is to find a quotient such that the quotient that I find times x minus 3 is equal to the original dividend. And we know that is true. If I were to check this, I would take the quotient, I would multiply by the linear term, which is the divisor, and I have to get back my dividend because I don't have a remainder. So this is q of x, and I can write this as x cubed minus 4x squared, this is my original dividend, plus 3 is equal to my q of x, which is x squared minus x minus 1, times x minus 3. Right? Excellent. Now, what have we shown here? That the factor theorem is just a specific case of the remainder theorem. The remainder theorem is a more general case. The factor theorem is a specific case when you have remainder 0. And it tells you that if you do get a remainder 0, if you have a remainder 0, then most definitely this linear term is a factor. X minus 3 most definitely is a factor of that function. And you can see here that you're able to find the other factor because then this quotient is a factor, and so is the linear term. And if this, let's see if this factors. X minus 1 would be -1 plus 1. No, this doesn't factor any further. But sometimes your quotient, you can go ahead and factor it, and then you end up with 3 factors instead of just 2 factors. Okay? So there you have it. I hope you understood this example and you're able to do your homework. You have some problems on your homework list that pertains to this kind of exercise. Okay? So I hope you've enjoyed this exercise, this example. You can check, you can multiply these two out, and you should get exactly this value. Hope this helps. Have a good one.